In this video, we're going to use formulas we've developed in recent videos to solve problem 2.3.11s. We're going to be finding the common effective annual interest rate I for two perpetuities, annuities that go on forever, one of which is arithmetically increasing. You've got two people here, Sandy and Danny. Sandy purchases a perpetuity immediate that will pay her, first of all, a first payment of $100 1 year from now. These are going to be annual payments. And each payment thereafter increases by a constant amount, 10. So the next payment would be 110, the payment after that would be 120, etc. Danny purchases a perpetuity due instead of immediate, which makes constant annual payments of 180. Using the same effective annual interest rate I, the present value of both perpetuities are equal. Calculate I, that common effective annual interest rate. All right, so here's Sandy's situation. Her first payment is at time 1. Now you certainly could write 100 here, and then 110, then 120, 130. However, it's going to be helpful to break this up into a form where we have formulas that we can use. We're going to break this up into two pieces, one of which is going to be a constant annuity immediate, and the other one of which is going to be a constant multiple of the increasing annuity immediate that we've talked about recently. You might think initially you should do maybe 100, then 100 plus 10, then 100 plus 20, then 100 plus 30. But it turns out to be better, for a reason I'll explain in a second here. So think of this as 90 plus 10, this is 90 plus 20, this is 90 plus 30, 90 plus 40, etc. Because now, for both of these two annuities that I've broken up the original one into, the present value is going to be evaluated 1 year before the first payment in both cases, and that's going to make it simpler. All right, so what is that present value for Sandy? Let's call it PV. Well, first of all, there's the constant annuity, the payments of 90. As an annuity immediate, its present value at time 0 is that constant amount, 90, divided by the effective annual interest rate, I. We've seen that formula before. What about the other one? Well, I hope you agree that a good symbol for it would be 10 times IA sub infinity. Increasing annuity, present value with infinitely many payments. That would be a good symbol for it, and multiplied by 10. What would the formula for this thing be? Well, really, it should be a limit as n goes to infinity of IA sub n. That should make sense if this limit exists, and it will. What was the formula that we've seen for that present value before? We've seen that the present value of this kind of thing was actually, first of all, the present value of an double dot, which is a little strange, because this is an annuity immediate, and this is the formula of the expression for the present value of an annuity due, but it is what goes there. Oops, sorry about that. And then I subtract n times v to the n, where v, as usual, is 1 over 1 plus I, and divide this by I. And I is the thing that we want to solve for. Let's continue simplifying this. An double dot is going to be 1 minus v to the n divided by d, where d is the present value discount rate. It's I over 1 plus I, minus nv to the n over I. This looks pretty complicated. It's not quite as bad as it looks. We can let n go to infinity, and these two things that I'm circling go to 0 as n goes to infinity. Now, it's pretty obvious, since v is between 0 and 1, that v to the n goes to 0 as n goes to infinity. It's perhaps a little less obvious that this goes to 0. It does. Basically, you've got a linearly increasing term involving n, and an exponentially decreasing term involving n here, where v is between 0 and 1. The exponential decay is going to win out, so to speak. To prove that requires L'Hopital's rule, but I don't want to go there. Just trust that this definitely goes to 0 as n goes to infinity, and that's something you really should know intuitively. Because of these things, this simplifies to, in the limit, 1 over I times d. But what is d? d is I over 1 plus I, so this can be simplified to 1 plus I over I squared, which is commonly written as 1 over I squared plus 1 over I, or the other way around, 1 over I plus 1 over I squared, it doesn't matter. So now, plugging this back up in here, I get 90 over I plus 10 over I squared plus 10 over I. I get simplified to 100 over I plus 10 over I squared for Sandy's present value. Now let's go on to thinking about Danny. He's got a constant annuity, and it's annuity due instead of an annuity immediate. So the first payment is at time 0, and it's constant 180, 180, 180, etc. The present value of Danny's annuity, as a constant annuity, you could write it as 180 times a double dot sub infinity. That would be 180 over d, where d once again is the present value discount rate. It's I over 1 plus I. Therefore, this can also be written as 180 times 1 plus I over I. And the equation we want to solve is the one we get when we set this equal to this. Multiplying both sides by I squared will get rid of the denominators and give us, hopefully, ultimately a quadratic equation. Let's see. Yeah, multiply this by I squared, you get, we didn't black down here, you get 100I. I'm multiplying that by I squared. Multiply this by I squared, you get 10. Multiply this thing by I squared, one of the i's cancels, you get 180 times 1 plus I times I, or 180I plus 180I squared. You can divide everything by 10 and rearrange. As a quadratic, you're going to get 18I squared. Let's see, 18 minus 10 is going to be 8I, and then a minus 1 equals 0. That's the quadratic equation that you must solve for I. We want the positive answer, so we better take a plus sign here. Negative 8 plus square root of 64 minus 4 times 18 times negative 1 is going to be plus 72. Over 2 times 18 is going to be over 36. That will become what? Let's see. Negative 8 over 36 is going to simplify to negative 2 ninths. And here we have square root of 136 over 36. So we want to approximate the answer it looks like here. Square root of 136. 136 to the 0.5 power. It's about 11.6619. Divide that by 36. And then subtract 2 ninths, which is approximately 0.22222222. And the answer is about 0.102. And that is correct. That is the approximate common interest rate to solve this problem, about 0.102.